All right, today we're going to dig into two technologies that promise to change everything. I'm talking about one that could power the entire AI revolution and another that could completely change what's for dinner. But, is the hype actually real? Let's take a look. Look, both of these ideas are wrapped up in these incredible, powerful stories. But they also come with some really big questions about whether they can actually work. So the big question we're asking here is this: how do you tell the difference between a real game changer and, well, an expensive dead end?
Okay, first up, energy. We're all hearing about how AI and data centers are just eating up electricity, right? This demand for power is getting kind of insane. And the proposed solution that's getting a ton of buzz: small modular reactors, or SMRs. The story goes that these are the clean, reliable power source we've all been waiting for.
So what exactly is an SMR? Well, think about a huge traditional nuclear plant. We're talking over 1,000 megawatts. An SMR is way, way smaller. But the real magic is supposed to be in the M for modular. The whole idea is that you can build these things on a factory assembly line, not out in a field on some massive construction site.
And this is where the story gets really good. The promise is, because you're building them in a factory, you can get an SMR up and running in just 3 to 4 years. I mean, compare that to the 10, even 15 years it takes to build a giant conventional nuclear plant. It's presented as the perfect, quick solution for our crazy energy needs.
I mean, the vision is pretty slick, right? It's basically like prefab homes, but for nuclear reactors. You mass produce all the parts on an assembly line, load them onto a truck, ship them out, and just snap them together wherever you need power. The dream is this scalable, plug-and-play solution you could drop next to a data center or even use to power a whole town.
It sounds amazing, doesn't it? A clean energy revolution delivered right to your doorstep. But here's the thing. After nearly 20 years of development, after billions of dollars have been poured into this, there's one very, very simple question we have to ask.
Zero. That's the answer. Absolutely zero. Despite all the headlines, all the hype, there are currently no commercially operational SMRs anywhere in the Western world. Now, you might hear about a couple of units in China, but the details on those are pretty thin. So, in the places where this tech is really being pushed, the number is a big, flat zero. And this timeline, wow, it really shows you how big of a challenge this is. One of the top companies in this space, founded almost 20 years ago, their design just got approved recently. And the absolute earliest, the most optimistic forecast for a single one to be up and running is 2030. A whole finished plant? Maybe 2034. Think about that. That's a nearly 30-year slog just to get the very first one online.
But, the timeline is only half the problem. The other issue, and it might be even bigger, is the cost. Early numbers suggest that power from the first SMRs could cost a whopping $590 per megawatt hour. To put that in perspective, that's 3 times more than a brand new large nuclear plant and almost 10 times the cost of onshore wind. And that's the catch-22, right? The cost only gets cheaper if you mass produce them, but mass producing a nuclear reactor is, well, it's an unbelievably massive challenge both in terms of engineering and just getting it approved.
And if history is any guide, even those crazy high cost estimates might be on the low side. I mean, these huge, complicated projects are famous for blowing their budgets. Just look at traditional nuclear plants. On average, they end up costing double what was originally planned. So when you look at that track record, you have to wonder what the real final price tag for these SMRs is going to be.
All right, let's switch gears and talk about our second case study, which you'll see has a similarly massive vision: lab-grown meat. And the promise here is just as big: to feed the entire world's growing hunger for meat, but do it without all the environmental and ethical baggage of traditional farming.
Okay, so it's really important we're clear on what we're talking about here. This is not the plant-based stuff you see everywhere in the supermarket, the burgers made from soy or peas. No. Lab-grown meat, or cultivated meat, is biologically the real deal. It is actual animal tissue. It just happens to be grown in a lab instead of on a farm.
And the story, just like with the reactors, is this perfect utopian vision. We could give everyone the meat they want, and demand just keeps going up, while using way less land, way less water, and cutting greenhouse gases. Oh, and of course, no animals have to be harmed. I mean, it sounds like the absolute perfect solution, right?
But turning that beautiful promise into an actual burger on your plate, it's an insanely complex and delicate process. So here's how it works. First, you take a tiny sample of stem cells from a live animal. Then you put those cells into this big steel tank. It's called a bioreactor. And you feed them this super nutrient-rich goo. You have to keep it at a perfect temperature for about a month, and over that time, the cells multiply and multiply until you're left with what is basically a meat paste.
So here's the massive problem, the Achilles heel of the whole thing. That bioreactor has no immune system. None! Unlike a cow or a chicken, it can't fight off germs. If a single rogue bacterium gets in there, it can just go wild and completely destroy the entire batch. We're talking thousands of liters of product gone. And that makes scaling this up a nightmare, because that risk is always there.
And if that wasn't enough, then you have the energy problem. So much for being a green alternative. Some analysis shows the process as it is now could be up to 25 times more energy intensive than just raising a cow. And it makes sense when you think about it. You're basically running a super sterile, super warm, pharmaceutical-grade incubator the size of a car 24/7 for a month straight. That just eats up power.
And this really gets to the heart of the scalability problem. I mean, to satisfy global meat demand, or even just a small piece of it, you would need an absolutely astronomical number of these bioreactors, all consuming unimaginable amounts of energy. When you look at it that way, with today's technology, it just seems impossible, both financially and for the environment.
Okay, so let's zoom out for a second. We've got mini reactors. We've got lab meat. What's the common thread here? Both have these incredibly inspiring stories about solving the world's biggest problems. But both are also running up against these huge, maybe even impossible hurdles with money and technology. And this really teaches us a bigger lesson about telling the difference between a great story and a great viable business. It feels like these kinds of things often follow the same playbook, you know? Step 1, find a massive global problem, like climate change or world hunger. Step 2, propose a futuristic, almost sci-fi solution. Step 3, wrap it all up in a really compelling, easy-to-understand story. And the focus is always on this gigantic future market, while the messy details of right now, like costs and whether it can even be done at scale, kind of get brushed under the rug.
Now, to be fair, there is another side to this coin. This is how innovation works, right? It's all about high risk, high reward. The argument is that this exact kind of uncertainty is where you find the biggest opportunities. I mean, think about it. The internet, electric cars. Every truly revolutionary technology probably looked like an unprofitable, futuristic pipe dream at some point.
And that brings us right back to where we started. Yeah, the potential for a massive payoff is there, but it comes with a very real risk of losing everything. So the key isn't to just shoot down every big, ambitious idea. It's about learning how to see past the flashy story, really dig into the numbers, and understand the basic economics of what's being proposed.
So we'll leave you with this to think about. Whether you're looking at the cost per megawatt hour, or the energy it takes to make a kilogram of food, or the fact that something might take 30 years to build, the numbers often tell a totally different story than the hype. So in a world that's just drowning in powerful stories, maybe the most important question you can ask yourself is, what are the numbers that really matter?